Well, hi everyone, and greetings from Northern Michigan. This is Bob the Science Guy. You know, I was looking at my friend Conspiracy Cat's channel the other day, and I saw that he was up to 22,000 subscribers. Boy, that's a lot. I only have 8,000, so I got to thinking, what's he doing differently? And then I figured it out. He does have something different.
Congratulations, Baldy Cats, on reaching 6,900 subscribers. And just remember, you should always do what a whiteboard tells you to do.
It's a whiteboard.
Why do you think that Conspiracy Cats guy uses a whiteboard so often?
Now, my first idea was probably not going to work out so well.
Watch your enemies, see them driven before you, and hear the lamentation of their women.
So instead, I decided to just get myself a whiteboard. Well, now that I have this new tool to help advance science, let's go see what we can do with it. Pretty slick, huh? Okay, so let's start talking about what perspective is. Now, if I have my eye about right here, and I'm looking out at an object that's on the ground, and that object is, say, that tall. Now, I'm going to see an angle that goes from there to there, and that's going to form an angle. That's my viewing angle. Now, if I take another object that's twice as far away, but the same height, I'm going to form another angle, like this. And that will have an angle. And this angle, right here, will be less than that angle right there. Now I'm going to do this one a little bit differently. I've got my eye, and then I have the ground. Now, instead of drawing buildings, what I'm going to do is I'm going to draw a line parallel to the ground. And then I'm going to put some stars or lights above and below at equal distances. Now, if I look up and down, I've got an angle. If I look up and down, I've got another angle. And if I look up and I look down, I've got a third angle. Now you notice that these angles, the further I go out, become smaller. So if that's number 1, that's number 2, and that's number 3, and they're all the same distance apart, I'm going to find that that angle is 1 over 1. That angle is 1/2 the full angle, and that angle is 1/3. With me so far? Now, if we go out here and we have 100 lights along through here at this same distance, and then we get out here to the 101st light, or the 100th light, I should say, we're going to form an angle that goes to that light, and an angle that goes to that light that will be 1 over 100, the size of this one right here. Okay, so when you have your eye, and you have the ground, and you have a line that is parallel to the ground, and then you have this series of stars up there, what happens is that these angles get smaller and smaller and smaller, as we talked about. But what if we go out here an infinitely far distance? So we'll have our dots, or our lights, and then we're going to form an angle that will be 1 over infinity, or essentially 0, the size of the original angle right here. So that will approach 0. Because it's so far away, it's blending into a point. Now, does that mean that we can see those two distinct points of light an infinitely far distance away? No, it does not. Because what happens is when you get light and you diffract it through a hole, like your pupil, you're going to get a pattern of light that'll have a shoulder, it'll have a big peak, and then it'll have another shoulder. This is what it looks like. Now, the second spot of light will be out here, and it will form the same thing. But what happens when we start moving these dots of light toward each other? What ends up happening is our first peak of light, which looks like this, and the second peak of light will come together, so that what happens is that big peak forms right on top of this secondary peak right here. And when that happens, when those dots are that far apart, you cannot tell them apart. And this is called the Rayleigh Criterion. And the Rayleigh Criterion means that you cannot tell two spots of light apart from each other. Now, I guess the next question that we would have would be, how far away would these two dots be before we couldn't tell them apart? Well, let's see if we can figure that out. First, we'll go ahead and draw out our situation. So, we've got our two parallel lines. We've got our eye right here. And we have a building. Well, actually, let's use the two lights, and they're right here. Now, we have an angle that forms as we look down and we look up, and that will form an angle. Now, the formula for the Rayleigh Criterion is 1.22 times the frequency of light in meters divided by the aperture size in meters. And that will give you your answer in radians. Now, 1 radian equals 57 degrees roughly. So let's figure this out. So, the critical angle right there equals 1.22 times the wavelength of light, which is 500 nanometers, or 500 times 10 to the negative 9 meters. Now that's the range of light that we can see is between 380 nanometers and 740 nanometers. So I'm going to use 5 as just kind of a median. And our pupil size is about 5 milligrams. Again, it varies from 1 to about 8. And that is 10 to the negative third meters. Now, that will equal the number of radians. Now, you can go ahead and do the math on this, but we're going to multiply the number of radians times 57 degrees, and we're going to come up with our answer. And our answer is 0.007 degrees. Now, that's the exact number. Another way that you can look at this is to say that it is between 20 and 30 arc seconds of angle. 360 degrees in a circle, 60 minutes per degree, 60 seconds per minute. All right, so let's go ahead and figure this out both ways. Let's do it the quick and dirty way first. Say we're shooting a rifle at a target that's 100 yards away. Now, 1 minute of angle equals 1.04 inches. Now, if you would like me to do a quick video to show how to determine minutes of angles, milliradians, and things like that, just leave a comment. So, 30 seconds equals about half an inch, and 20 seconds is about 0.4 inches. So, if we have two specks of light on that target 100 yards away, looking at it with our bare eye, that are 1 inch apart, we will see them as two distinct specks of light. If they are 1/3 of an inch apart, that is below the Rayleigh Criterion, and we would see those two specks of light as a single speck of light. We will not be able to tell them apart. And again, that's 1/3 of an inch apart at 100 yards with our naked eye. Now, to figure it out exactly, remember we have 1.22 times the wavelength of light over the distance or the diameter of the aperture. And we said that that would be 500 times 10 to the negative 9th over 5 millimeters would be 10 to the negative 3rd meters. Okay? Now, that works out to 0.007 degrees. So, if we look at an object that is 12 feet tall, for example, and we're forming an angle from the bottom of that to the top of it of 0.7 degrees. How far would this distance be? Let's go ahead and go to the triangle calculator. Okay, so this is the Math Portal right triangle calculator with explanation. Okay, so right here we can go ahead and pull up this triangle and we can solve for leg B, which is the bottom leg right here. We know that angle alpha will be 0.007 degrees. And we know that length of A will be 12 feet. So there's our answer. And here's how they got it. Now notice right here that the distance that we could see a 12-foot object is 98,221 feet. Now, if we take that number and we go to a calculator, Let's go ahead and get our numbers back here. 98,221. 98,221 divided by 5,280 feet equals. So that means that we would no longer see this object that is 12 feet tall at 18.6 miles. That's 18.6 miles. Now, just for fun, I went ahead and pulled up Walter Bisson's Advanced Earth Curve Calculator. I put in a elevation of 6 feet, my eye height, and a target size of 12 feet, and it says that we have lost all 12 feet of that over the horizon at just under 8 miles. Now, according to the Rayleigh Criterion, we should be able to clearly see both the top and the bottom of that for another 10 miles. But this is what is actually happening on Earth, and we'll go over that in a moment. Now let's just go over a couple of basics of perspective. Now, we already understand that if we have two parallel lines, one being the ground and the other one being a line above the ground, and we have our stars of an equal distance apart, and then we have an observer right here, they're going to form an angle to each of those stars, and that angle will progressively get smaller until it eventually approaches 0, which will be 1 over infinity, the size of this first one. Okay, so what will this look like in the front view? Now, if we were to look at the ground going out in front of us, and we were to compare the size of, say, these 12-foot buildings, the one that would be, say, 10 feet away from us would be yay big. The next, twice as far away, would be half the size. A third the size, a quarter the size. Now, what we could actually do if you wanted to, is you could kind of draw a line of perspective towards a vanishing point that went away, like that. Now, the ground underneath would also demonstrate this line of perspective going off to a vanishing point. Now, recall that we said that if this was 12 feet tall, we could not tell the difference between the top and the bottom at a distance of about 18 miles. Likewise, if this is 12 feet from down here to here, that would also vanish to nothing in about 12 miles. So, there has been a claim made that curve calculators do not take into account perspective. That's not true, because if you were to look at these buildings right here from the side, what you would see is a series of 12-foot buildings along the ground, and from an observer out here, you could actually draw these lines, right? And these angles that are formed would result in an angular size that is exactly what we see on the drawing going out away from us. So when we talk about perspective on a curve, where you have an observer, you have an object, and you draw a line that says, okay, well, this part is hidden and that part's visible. This is actually the same thing as this right here. And that is perspective, just as that is perspective. So I want to thank you all for tuning in. What I would like to talk about on the next video, which we'll also use the whiteboard on, is what the horizon would look like on both a flat and a spherical or curved surface Earth. And I think you'll enjoy it. Now, please put any comments in the video. I'll be watching this, and we'll go ahead and answer them for you. Take.
It holds too deep for me. Feel my brain getting real sore.